Hi, this lesson is about the laws of logarithms. So there are three laws or properties of logarithms. The first one is called the power law, the second one is the product law, and the third is the quotient law. With power law, it allows you to rewrite a logarithm where you're taking the log of an exponential expression. So I have the log base b of x to the nth power. That is equal to n times the log base b of x. So there should be a little b here in this corner. I think I forgot to write that. Because the logarithm on the left side and the right side have to have the same base. So it allows you to put the exponent in front of the logarithm. The second one, product law, says that if you have the log base b of x times n, it allows you to rewrite that as a sum of two logarithms. So it'll be the log base b of x plus the log base b of y. So you can separate these. And the third one is the quotient law, and that says that if you have the log base b of x divided by y, that is equal to the log base b of x minus the log base b of y. So here I have three examples, one for each. The log, this would be a common log. The log of 5 to the third is equivalent to 3 times the log of 5. And the second example here in purple says that the log, again, this is a common log, the log of 7 times x would be the log of 7 plus the log of x. And the third example, I have the log of 2 over 9 is equal to the log of 2 minus the log of 9. So these properties or laws, log laws, are used to simplify logarithms. In the future, you could use these in some derivative calculations. So these laws are definitely convenient. They make things, they allow you to expand logarithms. Might be easier to simplify them in that way or condense them when you go from the right side to the left side, which is used for other purposes. These rules are also good to know. They are helpful when simplifying logarithms. So the log base b of 1 is equal to 0. This would be true for any base. So for the example, the log base 5 of 1 is equal to 0. And the natural log of 1 is also equal to 0. And that is because 5 to the 0 power equals 1. And this one is because e to the 0 power equals 1. The second rule says that the log base b of b is equal to 1. And so as long as the base of the logarithm and what you're taking the log of are the same value, your answer will be 1. And so here are two examples. The log base 7 of 7 is 1, or the natural log of e is 1. And again, that is because 7 to the first power equals 1. And this one is because e to the first power equals e. And then the third rule says that the log base b of b to the n is equal to n. And that's, again, as long as this base and the base of here of this exponential expression are the same. So this is one example. The common log of 10 to the fifth, remember the base here is 10, even though you don't see it, that's going to equal 5. That's your n in this example. Or the natural log of e to the eighth is equal to 8. Again, the base here would be e. And so as long as this base and that are the same, it's just going to be the answer is your exponent. Okay, so definitely it will be necessary to memorize these logarithmic laws and these rules for logarithms in order to do a lot of the work regarding expanding or condensing logarithms as well as simplifying them. Okay, so here's our first example. The directions say to expand the log base 3 of 14. So expand means that I want to write this single logarithm into multiple logarithms. And so in order to do that, I need to rewrite this 14 as a product. And so 14 can be rewritten as 2 times 7. And so using my product law, this is equivalent to the log base 3 of 2 plus the log base 3 of 7. The next one says log base 8 of n to the 5th. Here I'm using your power law. So the only thing I can really do to expand this is to put the 5 in front of the logarithm. So I have 5 log base 8 of n. Okay, so next example is asking you to expand the log base 3 of the cube root of y divided by 7. In this example, I'm going to be using both the power law and the quotient law because the cube root of y can be written as an exponential expression, and I'm dividing by 7, so that's why I'm using my power law. So this is rewritten as log base 3 of y to the 1/3 over 7. So I apply my power law to the numerator, which is 1/3 log base 3 of y, and then my quotient law means that I can write this 7 here separately, so minus log base 3 of 7. So oftentimes you will be using one or more of the laws when you are expanding. And so this is an example of where I will be using all three laws. I have to use product law in my numerator for the x and the y. I have to use my power law because of the exponent associated with the z, and my quotient law because I have z cubed being divided by xy. So when you break that down completely, I have the log base 2 of x plus the log base 2 of y, that is your power law, and then minus, that's your quotient law, and then power law is applied to the 3 in front of that logarithm. So that's 3 log base 2 of z. For example 5, I again am going to rewrite this radical as log base 4 of x to the 1/7, and then the only thing you can do to expand it is to use my power law and put that as a coefficient, so that's equal to 1/7 log base 4 of x. Okay, in example 6, we're going to be able to do a little bit more. The directions say to expand and simplify. So I'm going to write this using my product law as the log base 2 of 32 plus the log base 2 of x squared, but then I can apply my power law to the second logarithm and put that 2 in front. So this logarithm becomes 2 log base 2 of x. And the reason why this logarithm becomes a 5 is because I'm using what I know about logarithms. 2 to what power equals 32? And the answer is the number 5. 2 to the 5th power is 32, so 5 would be the answer for that logarithm. Remember, evaluating a logarithm, if it can be done without a calculator, like we can in this case, is just the exponent associated with the base. Okay, for number 7, again, I'm going to use one of the laws, but this time I'm using the quotient law. Remember, here I have negative log base b of r plus log base b of v. So typically when we have an addition, we use the product law, but this could actually be rewritten differently because of that minus in front. This is equal to the log base b of v minus the log base b of r, which means quotient law applies. It's log base b of v over r. For the following examples, I'm going to I'm again condensing. So condensing is the opposite of what we were doing previous. We were taking multiple logarithms and collapsing it down into one. So here I need to do the same thing, but there is a little bit of a shortcut that you can take. This is log base 4 of 3 to the 3rd plus log base 4 of 9. In order to condense this, I need to use my product law. And one option, and this would kind of be, I guess, the harder way, would be to do 27 times 9, because 3 to the third is 27, and a sum of two logarithms will become the product of those two expressions, the log of the product. And then you would multiply that out. But I did it a different way. I rewrote the 9 as 3 squared. And so when I have this product, you can actually add your exponents. And so that's 3 to the 5th power. 3 to the 5th power is the same as 27 times 9. And so you end up with a log base 4 of 243. So either option would work to give you the same result. Number 9, you're asked to condense log base 2 of 3 plus 1/2 log base 2 of x. So I will be using product law, and I will also be using power law. The 1/2 is associated with the second logarithm. So I have log base 2 of 3 plus log base 2 of x to the 1/2. So this coefficient becomes an exponent, again using power law. And we know that anything to the 1/2 power is just a square root, so the second logarithm gets written like this. And then a sum becomes a product. So this collapses down or condenses down to log base 2 of 3 times root x. Here's another one that's similar. I have to use power law because of this coefficient here and this coefficient, and quotient law because of that minus sign. So using my power law, I will get this log base b of a to the 1/2 minus log base b of 5 to the second. And then the minus means I'm applying my quotient law. I rewrote the a to the 1/2 as the square root of a and then divided by 5 squared, which is 25. So it condenses into one single logarithm, log base b of the square root of a over 25. In this one, you're just being asked to simplify. And in order to simplify this, you do have more than one option. I'm going to do this one here using my logarithmic laws. And so I'm going to write this quotient as the difference of two logarithms. And then I'm going to apply some of the rules that I mentioned at the beginning of the lesson. 81 can get rewritten as 3 to the 4th power. So this logarithm is equal to 0, and that is because 3 to the 0 power equals 1. The answer is the exponent. And this was another rule that I mentioned. When these two bases are the same, this one and this one, it's just equal to the exponent. And so this will be 0 minus 4, so my answer is just negative 4. This could have also been done in a different way that would give you the same result. Using what we talked about in the first section in chapter 4. 3 to what power will give me 1 over 81? Okay, 1 over 81 is 1 over 3 to the 4th. But we know that we can rewrite the 1 over 3 to the 4th, and I'll just call this x instead of a question mark to make it more mathematical. And so then we get that x must then equal negative 4. Same answer we got here. So either way, you end up with the same result, and both results are correct. Or both methods are correct. So number 12, log base 5 of 5 to the 0.1, it's basically applying the same rule I applied here. My answer is just the exponent, which is 0.1. And that was, again, the third rule of the 3 rules that I gave at the beginning of the lesson. Okay, then number 13 is really the same rule. I have log base 6 of the cube root of 6. So the cube root of 6 is the same as to the 1/3 power. So this can get rewritten as 1/3 log base 6 of 6. But again, this was one of the rules I mentioned was the second one. This is equal to 1. And so 1/3 times 1 gives me a final answer of 1/3. All right, so here we're going to use the laws of logarithms to condense as much as possible, then evaluate it. If a calculator is needed, then round to the thousands place. So you might need a calculator for some of these. So I have log base 4 of 2 plus log base 4 of 32. I'm going to condense this by multiplying the 2 and the 32. So it's log base 4 of 64. But 64 can be rewritten as 4 to the third power. Here's that rule again. When these two bases are the same, your answer is just the exponent of 3. Part B, immediately to the right, is log base 2 of 5 minus log base 2 of 80. Here I'm using my quotient law. This is log base 2 of 5 over 80. But 5 over 80 reduces to 1 over 16, so I have log base 2 of 1 over 16. The 1 over 16 can be rewritten as 1 over 2 to the fourth, but then again, I can use my rules for exponents and write the 1 over 2 to the fourth as 2 to the negative 4. Again, there's that rule where I have the same base in both places, so my answer is just the exponent negative 4. So far we didn't need a calculator for any of these. Here I have negative a third log of 8, and so when you don't see a number in the corner for the base, that means it's a common log. It's a base of 10. So using my properties or my laws, this is the same as the log base 10 of 8 to the negative 1/3, which we know is the log of 1 over 8 to the 1/3. To the 1/3 power means the cube root of 8. The cube root of 8 is equal to 2, so I'm taking the common log of a half. So I cannot write 1 over 2 with a base of 10. So at this point, you would need a calculator, and you do have common logarithms in your calculator. So you just take the log of a half, and you should get an answer rounded to the thousandths place of negative 0.301. So we can use logarithms to calculate either very large numbers or very small numbers. And that's another application of logarithms that's very convenient. There are some numbers that if you put into a calculator, you will get an error. Sometimes they call it overflow error because the number is just too big or too small for the calculator to handle. And so logarithms give us a way around that. And so this would be an example of a number that would be very, very small because my denominator is a very large number. 73.4 raised to the 86th power would be a very, very large number in the denominator. So a relatively small number divided by a very big number becomes a very small number. So you can try putting that into a calculator. You probably will get some sort of error. So we use logarithms, and I'm going to use common logs. So I take the log, I'm going to let n equal the original number, and I'm going to take the log of both sides of the equation. So I have the log of n equals the log of 895 over 73.4 to the 86th. The right side gets manipulated by using your logarithmic laws. I use the quotient law and the power law. So I have the common log of 895 minus 86 times the common log of 73.4. Now at this point, you can do these two calculations in your calculator, and it should give you a number like this, negative 157.49803881. I don't think I rounded there, pretty much put everything that was on the screen. But remember, that is not the value of this number because I took the log of both sides. So the log of that number equals this. So in order for me to solve for n, I have to raise that number or put 10 raised to that number. So this is now the value of that. Okay, which can be broken down even more using what we know about scientific notation. So the first thing I did was I rewrote this expression as the log of negative 157 times the log of negative 0.49803881. Remember, the sum of these two numbers, of this exponent and this exponent, gives me that exponent right there. But now the 10 to the negative 157, we're going to leave that alone because that's going to be a nice way to present it in terms of scientific notation. And if you plug this into your calculator and round it, you should get 0.318. So I rounded it to the thousands place times that number. Okay, but typically with scientific notation, you put your decimal immediately to the right of the first non-zero digit. So instead of 0.318, I put 3.18. And since I moved my decimal in, that means I would have to go 157 places to the left plus one more. So it's going to be 3.18 times 10 to the negative 158. So if you can imagine inserting zeros in front of the 3 and moving your decimal 158 places to the left, this is a very small number. Okay. Here's another one. I have 126,000 raised to the 20th power divided by 2.63 raised to the 2.5 power. In this case, this result would be a very large number. That numerator is much bigger than whatever that denominator is. So when you divide them, it's still going to be a very large number. And again, if you just put this directly into your calculator, you should probably get, I would think most calculators would have trouble with that. You would get an error, or sometimes they say overflow error. So again, we use logarithms to help us. So we set an equation. Let n equal the original number and then take the common log of both sides. My logarithmic laws allow me to rewrite the right side. I use the quotient law and the power law as 20 log of 126,000 minus 2.5 times the log of 2.63. This entire thing can be computed in the calculator, and you would get 100.9575215. But again, that is not the value of this number. It is the value of the log of that number. So that means that this is the exponent with a base of 10. So it's 10 to the 100.9575215. And then I used a similar trick to what I did above. I rewrote this as a product of two exponential expressions because you add your exponents when you write them as a product. 10 to the 100th can be left as is, but when you put this into a calculator, you get 9.07. So 9.07 times 10 to the 100th is your answer, which is, again, it's a very big number. If you can imagine moving your decimal 100 places to the right and adding in, you would need to add in 98 zeros. This would be a very large number. Okay, so that's a way of getting an answer without relying on the calculator to just compute that for you. So as I've mentioned in the past, your calculator has a common logarithm and a natural logarithm, but sometimes you have to evaluate a logarithm with a different base that cannot be done manually. So there is a way to convert logarithms of a different base into another base, and typically we convert it into either a common log or a natural log so that we can evaluate the original logarithm. And so the general formula, called the change of base formula, says that if you have a log of base b of x, that is equivalent to the log base a of x, so this x will be the same x here, divided by the log base a of b. So whatever your base is in the original, that's what you're taking the log of. And this log of base a on the right, Like I said, typically you would want that to either be a common log or a natural log on this side so that you can use your calculator. So use the change of base formula to evaluate the log base 2 of 16, then round to the thousandths place. This is an example of something that you would not be able to do by hand because you cannot write 17 as 2 to some exponent. If you were asked for the log base 2 of 16, well, that I could do by hand because 16 is 2 to the fourth and my answer would be 4. But 17 cannot be written with a base of 2. So I will need technology. And I don't have a log base 2 in my calculator. So I'm going to use this formula. So I'm going to convert this to a common logarithm. So using this formula, it's the log of 17 divided by the log of 2. This you can plug into a calculator, and so that means that log base 2 of 17 is approximately equal to 4.097. You would get the same answer if you use natural logarithms instead of common. So if you did the natural log of 17 divided by the natural log of 2, that also gives you 4.087. So which one you choose, common or natural, doesn't matter. The ratio of the two will give you the same result. So in this next example, it says to compare the calculation of the natural log of 0.5017 to the calculation using common logarithms and the change of base formula. So if you just plug natural log of 0.5017, I'll get negative 0.6898. If I convert this using this formula to a common log, that would be the common log of 0.5017 divided by the common log of e, because remember the base here is e, and that's what you should be plugging in, the base in the denominator. And if you did that computation of that ratio, log of 0.5017 divided by the log of e, you get the same exact answer as you did in the first calculation. So that's to show you how change of base formula will work, no matter what your situation is. So here's another logarithm with a base of 12. Again, I cannot write 122 with a base of 12, so I do need technology. So this time I'm going to use natural logs. This will be the natural log of 122 divided by the natural log of 12, and you get 1.933 when it's rounded to the thousandths place. Your other option would have been to do the common log of 122 over the common log of 12, and you would have gotten the same answer. So you don't have to do it twice. Just pointing out that either one would give you the same result. So we want to use a graphing calculator to display the indicated graph of y equal to 2 log base 8 of x. So like I said, a graphing calculator and also graphing calculator apps would only have a common log or a natural log, and this one is a log of base 8. So I'm going to need to use my change of base formula in order to write it in a different way. So I use natural logs. So this is the same as 2 times the natural log of x divided by the natural log of 8. 2 is just the coefficient. So this can be entered into a graphing calculator, and you would get this graph right here, which looks pretty familiar. It looks like the typical shape of a logarithmic function. But I wanted to show you that you get a different result when you do the next example, which should be the same, but it doesn't quite work out the same. Remember, if I use my logarithmic laws, this 2 becomes an exponent of x, just like I have here. So if I rewrite this using common logs instead of natural logs and putting the exponent, the coefficient in there for x, the log of x squared divided by the log of 8, well, this is the picture, which looks pretty different from this. And that's because when I square the x, the domain of my logarithm completely changes. In this case, my domain is just all positive numbers. That is what the domain of a logarithm typically is, and my range is all real numbers. So remember, you can't take the log of 0, you can't take the log of a negative number, you would get an error. It doesn't exist. But once I square my x, then negative numbers are okay because a negative number squared is positive. So that's why your graph is on both sides of the y-axis. In this case, my domain is from negative infinity to 0, and then again from 0 to infinity. Your range doesn't change. It's still all real numbers. And so again, that was the same graph that I did earlier. You can see how they are different domains, different result. So why are the graphs different? Again, because the domains are different for this situation versus this situation. Here you can plug in negative numbers, and in the other one you cannot. Okay, so that's it for this lesson. Good luck.